Well, this again is from Stuart's talk at the Alvarez Symposium a couple of years ago, in a couple of months. And he's here explaining a little bit about his experiment. Actually, it's sort of gotten off the edge there, hasn't it? But in any case, I'm going to talk not as much as I might have about the context for his experiment, because Steve Chu covered that, but I'm going to go through it. I'm going to focus primarily on the experiment itself, and then I'm going to say a few words about basically the interaction between Stuart and John Clauser, which was not an easy one. This slide also was shown at the symposium, and Stuart referred to this slide as having him there dressed as a graduate student, which he certainly was. I'm going to go relatively quickly through the precedents of the experiment. This is John Bell's paper which contains the theorem, what's called Bell's theorem, that one could actually do experiment. Well, it wasn't about an experiment. The theorem stated that at certain angles, if you assumed hidden variables, the assumption of hidden variables would conflict with the predictions of quantum mechanics. John Clauser, well, here I have a couple of slides like this. Forgive my handwriting. This is basically Bell's analysis. This is the pair of spin-and-a-half particles case. And as I said, his paper has a section that says contradiction. That's the title of the section, and it leads to a contradiction between hidden variable theory and quantum mechanics. Clauser's paper of a few years later expanded what Bell had done and focused on an experiment that could actually be performed. And that experiment was an extension of an experiment by Kocher and Cummins, which actually demonstrated entanglement. Okay, I say that because some people say that the Friedmann-Clauser experiment was the first thing to demonstrate quantum entanglement. That isn't quite true. It was the first experiment to demonstrate quantum entanglement without hidden variables. That is, it showed that hidden variables did not account for it. Okay. Now, basically, the experiment proposed by Clauser and company was, as I say, an extension of Kocher's experiment, which used a two-photon cascade in calcium in which the cascade goes from a spin zero state down to an intermediate state, and then back to the ground state, which is a spin zero state, as a result of which the two photons have to be in a spin zero state together, okay? And this is just Stuart's rendition based on Bell's later paper about hidden variables, that if you consider that case, you can write the state function for the two particles as another somewhat familiar looking thing having to do with right and left circularly polarized photons. But you can then go down and express it this way, which is linearly polarized photons. And again, this has the same familiar structure as the two spin-and-a-half particles had. Now, Kocher and Cummins ran their experiment, which again used the calcium case, at 0 degrees and 90 degrees, and its purpose was to demonstrate that quantum mechanical prediction of entanglement was the case, okay? But it was not done at the precise angles, which are 22.5 degrees and 67.5 degrees, in which the experiment would be most sensitive to the differentiation between a hidden variable case and a non-hidden variable case. So that's why they proposed to extend this experiment, also make it more robust so that it had better counting statistics, better polarization of the photons and so forth. So the results were reported in this paper, Friedman and Clauser, 72. The calcium level diagram is this. The experiment uses an arc lamp to populate a state with this 2200 angstrom photon, which then branches partly through a spin zero state. One photon, the 5500 angstrom photon, is emitted, and then immediately a 4200 angstrom photon is emitted, and those are the two photons that they're looking at in this experiment. Now, so what they measured as a function of phi, I guess, the angle between planes of linear polarization of these two polarizers were the following quantities. The coincidence rate with both polarizers in, and the coincidence rates with one or the other polarizers removed, and that's an impressive feat in the context of this experiment. And finally, the coincidence rate with both polarizers removed. This is basically establishing what the background of coincidences that are just random, okay? And in Clauser's paper, or connected with Clauser's paper, was this so-called hidden variable inequality, which said that this combination of those rates had to lie between -1 and 0, okay? That could be simplified for these two specific angles into something that's sometimes called the Friedman inequality, that says delta, this quantity, the difference between these two rates, -1/4, was less than or equal to 0. And those two angles are the ones that we're expecting to exhibit the greatest discrepancy between a hidden variable theory and pure quantum mechanics, okay? And the result, just to tell you the story in terms of this, that Friedman and Clauser got was that delta, that quantity, was indeed greater than 0. It was 0.050 plus or minus 0.008, which is 6 standard deviation experiment, okay? Which is robust. Somebody told me that Luis Alvarez didn't much like to hear about 2 and 3 standard deviation experiments. He liked to hear about 5 or 6. So this probably satisfied Luis. Okay, so this is the experiment in principle, how it worked. Above, at the top, you see a calcium oven, and a stream of calcium atoms passed through the center of the experiment with polarizers and detectors on either side. Below the reaction chamber was a deuterium arc lamp, which is what supplied the excitation photon. And then it's shown a simple diagram of the electronics and so forth. I have to say that in reading Stewart's thesis, I was really impressed with the care with which he and Clauser devoted to the various components of this apparatus, including types of arc lamps, and subsequently Stewart's, many years later, he said he was happy to have forgotten most of what he learned about arc lamps. Care in terms of the photomultiplier tubes, the lenses, and of course the polarizers themselves. I was really impressed with how robust this experiment was physically, because this thing, you saw that photograph with the long things on either side of the reaction chamber. Well, let me actually show you a couple of pictures. So this looks down on the reaction chamber, the circular area. To the upper right in this photograph is the calcium oven. So the stream of calcium atoms goes through the chamber and is collected on this side. The arc lamp is under the chamber, so you don't see it here. And then there are vacuum pumps and so forth. Now this photograph is of one of the polarizers with the light shielding removed, so you can actually see the pile of plates polarizer inside. What's really impressive about this thing is you see this large gear with the funny shapes symmetrically around the circle. It's called the Geneva gear, and this was the way this enabled them to change the angle by exactly 22.5 degrees, pi over 8, and then go to the next one, and it latched right into that, okay? Both of these polarizers on both sides rotated at 360 degrees, okay, during the experiment, and it did it automatically. That is, this thing was run by a console of some sort that the runs were 100 seconds long, and then it would change. It would change the angle of one or the other or both of the polarizers. Some of the runs had the piles of plates removed. That is to say, I referred to measurements without the polarizer present. So there's this fancy, well, complicated, I guess I would say, rigging for actually pulling the plates out of the line that the photons would go through. And this thing ran 24 hours a day, basically. One of the amusing things that I saw in an interview that Stewart had with a writer named Louisa Gilder, who wrote a book called The Age of Entanglement, was that Stewart mentioned that at his thesis defense, Charles Townes complained about how much data they had taken. He said, "Why did you spend so much time on it?" Well, one reason was to satisfy the 6 standard deviation Alvarez criterion. But I mean, it really was an impressive thing that this rather complicated device was automatically running, rotating the polarizers, pulling the plates out appropriately, and collecting the data. Now, the data collection aspect of this was rather crude because they had to have punch tapes. I mean, this data was coming out on paper tape. They had to run it over into another room where the computer was. And they talk about running back and forth with baskets full of data. Well, I'm not sure exactly. I can't quite picture that, but that's what they say. Okay, so here is a representation of one way of looking at the principal results. This is the measured count rate as an angle of phi. Again, the angle between the planes of polarization of these two polarizers over the entire 360 degrees. The data points are obvious with their error bars. The curve is a calculation, not a fit to the data, a quantum mechanical calculation. So this alone actually shows that for all of these angles, it fits the quantum mechanical case. The next slide takes part of that data and calculates this quantity delta phi that I referred to as the Clauser inequality, okay? And that Clauser inequality said that at 22.5 degrees and at 67.5 degrees, that was the critical area for determining whether or not there could be hidden variables. The hidden variables inequality requires that all the data be between the two dashed lines, okay? The fact that at those angles, it obviously exceeds those boundaries is a visual demonstration that hidden variables, local hidden variables, were not involved. This is just a repetition of what I showed you before, this 6 standard deviation result. Okay, now I just want to say a few words about the interaction between Stewart and Clauser and some things that I found a little puzzling and I'm still pursuing. When I looked up did searches on the web, I quickly came up with an interesting piece by a guy named David Kaiser at MIT, who's a professor of physics and of history of science, who had just written a book called How the Hippies Saved Physics. Don't worry about the title. It's about a group of physicists in Berkeley who had interests in these sort of peripheral, what were considered peripheral issues of physics. But what got me was that I'd actually seen the book before, and I looked up my friend Fritjof Capra in it just to see what it said. He and I used to live across the street from each other for about 20 years. But when I went back looking for what it said about this experiment, it described this as first Clauser's experiment. It said, it didn't mention Stewart's name in the text. It did have a reference to the paper. So Stewart's name was in the back of the book. It referred to Stewart, it kept referring to Clauser and his student. So I knew he wasn't Clauser's student. He was Gene Cummins' student. Another thing that it commented on was that, and I found that Clauser was fond of talking about putting together things with duct tape. And the text actually says that in a short time, Clauser duct taped together an apparatus that succeeded in demonstrating this, what we've seen here, that hidden variables were not the reason for the quantum mechanical entanglement. Well, there is duct tape here. You see that it's actually it's used as part of the light shielding. It's holding you can see along the edges of the polarizers. But duct tape doesn't make a very good vacuum seal, as most of you know. And you see the apparatus in the middle. That's where the excitation chamber and so forth are. They're not duct taped together. So actually I had a conversation with Clauser. I said, how could you say that this was duct taped together? And he said, well, we went to a room that had, maybe it's the Beam Group's supply of vacuum pumps, okay? And I was like, these pumps were around. They didn't buy them specifically for this experiment. And then he mentioned the counting electronics. He said, we went to the pool of counting electronics and got that. To me, that wasn't duct taping anything together. I mean, you used vacuum pumps and counting electronics. And so this seemed very strange to me. Well, I'm going to close because I'm sure I'm over time now. There was an interesting thing in this lengthy interview that Louisa Gilder conducted with Stewart in 2000, and there was something quite funny. His humor comes through in these interviews, even though he's talking about all of these different people doing different things and being confused about what was going on and so forth. But at one point, he stops and he says, "Do you need a hero?" And Gilder says, "What's a hero?" And Stewart says, "Do you need a hero for your story? Because I'm available." So Stewart remains a hero to all of us. And that's all I wanted to say. Thank you.